work today is what we have been pursuing over the last a little more than a year with Hitoshi, who was sort of starting this reconsideration of looking at perturbing the SUSY exact results. Also Ofri Talan, who is now I still have Berkeley here. He just moved now to the Hebrew University. He's a professor there. And my student Andrew Gomes, who is going to move as a postdoc next year to Lausanne, and two of Hitoshi's students in the last paper. And this is going to be a free Meson seminar. And actually, in my talk, there will actually be some free Mesons. So it's a really cool name, actually. I really like it. Very good. So I will give you first, for those who didn't grow up in the 1990s, a brief review of Seibergology and how to use it, and then a brief review of anomaly mediation. Then I will apply this method of perturbing Seibergology with AMSB to SUSY QCD. So this will be sort of the main part of the talk, and try to see, what kind of phases are we going to get when we are taking, the exact results known from supersymmetry, and then add a little bit of supersymmetry breaking and see how that actually changes the phase structure. And then I don't know how much time I'm going to have. I probably will just run through these relatively briefly. There I'll show you how to, get some exact results in chiral theories. And these, I think, are particularly interesting and important because analyzing chiral theories is really difficult, even on the lattice. It has a, it seems, very hard. So you can get at least some ideas of, what the phase structure of these theories will look like. That's pretty interesting. And then the SO series. So this one here will be for the SU series. And the reason why the SO is interesting is because there sometimes you can actually identify what the mechanism of confinement is. And in fact, we will see that for a large chunk of them, we will be able to see, the monopole condensation happening directly as the mechanism for confinement. Okay, so that's the plan. All right, let me hide this thing here. Good. Now it's much better. All right, very good. So I guess I probably don't have to convince you that one of the most important questions in quantum field theory and particle physics is to really understand the phase structure of strongly coupled gauge theories. And for example, nail down the mechanism of confinement, to answer the kind of questions, how many flavors can I add to QCD and still have confinement in the theory? And does it persist for a large number of flavors? Is there a conformal phase? Are there other phases realized? At least we know in non-supersymmetric QCD that there should be at least one kind of other phase, yes, which is the conformal phase, because very close to the boundary there, they lose asymptotic freedom. You can actually show that there is a perturbative Banks-Zaks fixed point. So, the expectation is that in the non-supersymmetric versions, there are at least these two. Now, as you see in the supersymmetric versions, there are a lot more. And then the question is, how are these related to each other? Very good. So now, this is an important question, but there are not that many tools available to us for studying it. Of course, the most important one is lattice gauge theory, though for chiral theories, it's still, pretty hard. I'm not really an expert, but, I think there are some progress, but it's not yet, as far as I understand, at the level of really being able to predict what the phases of those theories are. But anyway, lattice is, of course, at some point, all of this hopefully will be subsumed by lattice, and they will tell us whether, all our speculations or analysis were correct or not. Besides that, we have sort of, the anomaly matching conditions. So those are some really, strong strong tools that we can take advantage of. Now, for chiral theories, there was sort of, this is some story that is called tumbling, and that's something that was made up at the very late 70s, I think, by people like Susskind and Monopoulos, and it's sort of, it's a sort of a fairy tale of how to think about chiral theories and try to understand what the structure of it is. I will, if I get to the chiral theories, I will explain more what it is. It's not really, some exact tool. It's not like an anomaly matching. It's more like, a heuristic picture of trying to understand, what phases you should expect. And then there's the one that, I will be talking about today, is to extrapolate from the supersymmetric gauge theories. Okay? Because, of course, as you probably know, doing this story of nailing down the phase structure of supersymmetric gauge theories, in supersymmetry, is much easier because of the constraints provided by supersymmetry, mostly holomorphic. So this is something that for a vast number of supersymmetric theories has actually been done by Seiberg and many other people in the mid-90s. Then, of course, the question is, okay, so what do you learn about the non-supersymmetric theories by starting with the supersymmetric one? So this is the one that I will be focusing on today. Okay, so let's try to first give a quick review of what we know about the supersymmetric versions of these gauge theories. And as I said, again, it gives you a very powerful constraint on the strong dynamics. And Seiberg basically was able to nail down the phase structure of supersymmetric QCD itself in '94. That was his miraculous year, of course. Then he also did Seiberg Witten and all of Seiberg duality. And so the tools that are at our hand here, that the main additional tool that you have that you don't have in the non-supersymmetric theories is holomorphic. So depending on how much supersymmetry you have, some of the quantities have to be holomorphic, which imposes an additional constraint, which then together with symmetries, anomaly matching conditions often allows you to actually uniquely nail down what the phase of what the vacuum structure of a particular theory is. Not always, but sometimes you can actually do instanton calculations, so that's also a very useful tool. But it's only a very particular type of theories where this comes into place. And of course, integrating out and Hicksing the theories will allow you to move between the various versions of these theories with different number of flavors. And that is sort of an additional nice constraint, because if you sort of pin down the structure of one of those theories, then you can try to connect it to the theory with a smaller number of flavors or with a different gauge group. And ideally, then that's exactly what Seiberg did. You get sort of the coherent web of these exact results, and each of them on their own is pretty plausible, but what makes it really convincing is this whole web that you can really connect them in different ways and see that you are actually getting a consistent picture. Okay, and what is interesting is that actually, when you look at the phases of the supersymmetric QCD, which I will come to in a moment, you actually get many different type of phases depending on the relation between the number of flavors and the number of colors. Okay, so let's talk about supersymmetric QCD first. So I will be basically always talking about n equals 1 in 4 dimensions. So it's 4 supercharges. And we are going to talk about an SUN gauge theory and a certain number of flavors F. So this is the table of symmetries for supersymmetric QCD. And so you have the gauge group here, SUN, and then you have F fundamentals, so quarks, and F antiquarks that will give you an SUF plus SUF flavor symmetry. Then you have global U1 symmetry, and it's a supersymmetric theory. So you can also have a U1R global symmetry. Okay? And if you require that this is anomaly free, then this will be the chart assignment of that. Okay. Now another really nice property of the supersymmetric theories is that they have a moduli space of vacua often, yes, which means that actually, you know, when you have these kind of superfields, their scalar components, they are often flat directions along which there is no potential generated in these theories. So those are called the B-flat directions. And those are actually parameterized by the holomorphic gauge invariants. Okay, so what does holomorphic gauge invariant mean? It means you take chiral superfields and you just make gauge invariants out of them without taking complex quantities. Okay, so that's what the holomorphic gauge invariant means. So generically for SUN, these will be the so-called meson and baryon type fields. So in mesons, you know, you just take the invariant out of a quark and an antiquark. Yes, so this bar doesn't mean complex conjugation. It means, you know, to take a chiral superfield that is in the anti-fundamental representation, which you call the antiquark. Yes, so that's a meson field, and then the baryons, you know, you take just depending on what the gauge group is. Yes, you take n of these quarks in an antisymmetric representation. And these, of course, so the mesons exist for an arbitrary number of flavors. The baryons exist only if there are enough many baryons such that you can make an antisymmetric invariant. And so you have to have the number of flavors to be at least equal to the number of colors. Otherwise, you know, these baryons will just be vanishing. Okay. Very good. So here is what Seiberg found in '94. So this is the phase structure of QCD, of SUSY QCD. And again, as I outlined, you know, there are lots of different possibilities here. So I'm going to go through each of them. So don't, if you have never seen this, you know, I will try to quickly explain, you know, what the various entries actually are and what the relevant dynamics is that is giving rise to these phases. So here we are changing the numbers. So it is always SUN gauge theory with an increasing number of flavors. So here I start with 0 flavors and I go up to 3n flavors. Once the number of flavors is bigger than 3n, the theory will not be asymptotically free. Yes, so the theory will be IR free. So there's nothing exciting there, you know, about 3n. And so the question is what happens below that. Okay, so let's start with the flavor-less theory, pure super young mills. So this is SUSY QCD, but no matter. Of course, there's still, you know, some fermion there, yes, because, you know, there's a gaugino for the to make it supersymmetric, yes. So there's no continuous flavor symmetry, but there will be a discrete R symmetry. So it's a discrete subgroup of the U1R symmetry that is left there once the number of flavors is taken to be 0. And so this R symmetry is just rotating the gauginos. Okay, so it's essentially a symmetry on the fermionic partners of the gauge fields. Okay, and the dynamics that happens here in this pure super young mills is gaugino condensation. Yes, so the theory will actually give rise to confinement, and there will be a gaugino condensate that is generated in the vacuum. So the lambda is the super partner of the ordinary gauge bosons, the gauginos, and there will be a gaugino condensate formed. Because of that, there will be a superpotential generated for the theory. Of course, you know, the gaugino condensate can have, you know, so the Z2N symmetry is spontaneously broken to, I guess, what is it, to Z2, I think, or something like that. So there will be n possible values of the gaugino condensate. Yeah? So this omega k here is just the nth root of unity that comes into the various possible vacua, and then this is the superpotential. And this theory will be truly confining in the sense that if you are trying to calculate, what a Wilson loop would actually do for you, yes, you are actually going to get, you're actually going to get an area law, and so the potential between the test charges, if you took, this SUSY QCD pure Young Mills, I take two test charges, then the potential between these test charges would actually be a linear potential. So to truly confine it. Okay, so that's if there are no flavors. Okay, now if there are some flavor, but the number of flavors is relatively small, then something weird is happening. So there will be a so-called ADS superpotential. This is with a capital D and stands for Dine, not there. This is Affleck-Dine-Seiberg superpotential that is generated, and there will be a runaway vacuum in the theory. Okay, so what happens here? So this is one of the few results that was already present before 94. So this is something that was found by Affleck-Dine-Seiberg in 84, actually, 10 years before all the other results. So what will happen here is that the strong dynamics will actually generate a non-perturbative superpotential. And it's a pretty weird superpotential because there is a determinant n. So this is the Meson superfield, yes, the one that is made out of a QQ bar. And that's going to show up in the denominator of the superpotential. And that's going to be generated in the theory. So you see by what I mean by this runaway vacuum, that there is a field that is showing up in the denominator of a superpotential, yes. And so that means that this potential is going to become smaller and smaller as we go to larger and larger field values. So the vacuum is going to be pushed to larger and larger field values. So that's what I call a runaway vacuum. Okay, and the nice thing is that this particular term, for one particular case, that the number of flavors is exactly equal to the number of colors minus 1, is actually generated by an instanton calculation. And this instanton is sort of, the textbook example of the calculable instanton contribution. It's a really nice one. So this was, again, this was done in several people. And the reason why it's calculable is, yes, because, you have this determinant m in the denominator, and that actually tells you that the gauge group is going to be broken. So the gauge group is going to be broken before it becomes strongly coupled, yes. So this is actually, one of those examples where the instanton is deeply coupled and the gauge group is broken. So you can actually do a reliable instanton calculation and obtain this result. So here I have just outlined, how that instanton looks like. So you have to have zero mode, and then you have to close them up with all those interactions, etc. And you're going to be able to show that you exactly get this result holomorphic. Yes? So that's actually something that is pretty cool. Yes, but after you do the integral over the size of the instanton, you are actually getting a holomorphic quantity. So that's something that is quite non-trivial. And it only happens for this particular number of flavors. Okay? So the gauge group is Higgs, as I said. If the number of flavors is less than the number of colors minus 1, then the gauge group is not completely broken. The mechanism for generating the superpotential is not going to be instantons, it's something different. It turns out that in that case, actually, going to be a gaugino condensation in the unbroken loop. Yeah, so if I have less than n-1 flavors, and there's always at least some part of the gauge group that is left unbroken. Yeah, so then in that part, if you go out somewhere in the moduli space, there's an unbroken gauge group, and in that gauge group, there's going to be a gaugino condensate, and that gaugino condensate will depend on the dynamical scale of the unbroken gauge group, which will be matched exactly via this matching condition. So this expression here is exactly going to be the lambda cube superpotential that I showed you on the previous slide for the unbroken part of the gauge. And so when the number of flavors is less than n-1, then the exact same term in the superpotential is interpreted slightly differently. It's a different dynamics that is giving rise to it. Okay. Now, what is the phase of the theory? As well, there, the gauge loop is broken. At least for f equals n-1, it's completely broken. So, there is no potential between the test charges because the gauge fields are going to be massive, and there is an exponential decay. So you can think of it as just essentially no potential or constant potential.
Sorry, yes. Last thing was this is a d2 theta w squared rotation. W1 with the coupling constant being.
So this is a superpotential term. Yes?
Yeah, but you were explaining how you got it from.
Right. So it's this term here. It's this lambda cube. It's just this lambda cube. Yes, you do the matching of the, so you go out somewhere far in the module, you turn on, you just ask, okay, what happens at the random point in moduli space? So let me turn on the maximum rank for M. There's some value for determinant M. Okay, then the gauge loop is broken, let's say SU10 to SU7, yeah, so to SU3 or whatever, yes. There's some unbroken gauge loop because you didn't have many flavors. Now you ask, what is the coupling of the remaining, and that part now has no flavors, so it's connected exactly to pure angles. And so then you do the matching of the couplings, and the matching of the coupling now is going to be happening at the scale, how far you went out on the moduli space. And so the lambda to the beta of the low energy theory is going to be proportional to lambda of the high energy theory divided by the determinant M, which is providing the scale. So it's actually just this lambda cube.
No, I was wondering, in the UV theory, there is a d2 theta W1 by W1.
Right.
And you're plugging this into that.
So you can think of this also. So if you're asking where did the lambda cube come from, yes, that's where the lambda cube is coming.
I was wondering.
So I already took the result that okay, the pure angles is a lambda cube superpotential, yes. Good. And then the question is, where does that come from? Yes, that is coming exactly like you said. It's coming exactly from there.
From the d2 theta.
Right. You see that, yes. So this is the lambda, yes, and. All right. Very good. Now there are these two really weird ones. Okay, so these are two special cases, f equals n and n+1, and let me quickly explain what these do for you. Okay, so both of these have descriptions in terms of complete gauge singlet baryons and mesons. Given f equals n, then the theory is what is called the quantum modified constraint. Okay, so it's going to be essentially the theory of almost three mesons. Yes, so here they are all, except there is a constraint between the mesons and the baryons. So if you look at the theory in terms of quarks, yes, then the determinant M is equal to BB bar. Okay, if you write out this expression in terms of the underlying fields. But the claim is that the right dynamic, so this is what Seiberg found, and I think this is the thing that took him 10 years to understand. That he always guessed that it's gonna the right description of this theory will be that the mesons and the baryons actually become the right dynamical degrees of freedom for the theory. But there is a subtlety here, yes, the fact that actually, there was a classical constraint among the meson and the baryon. So you write out determinant M just in terms of QQ bar. You can check that classically determinant M equals BB bar if you write it out in terms of quarks. But if you think in terms of these becoming sort of like, composite degrees of freedom, yes, then what he found is that actually the relation between them is going to pick up a quantum modification. Okay, and this one, again, you can show that this is an instanton effect. So this has exactly the right power to be a one instanton effect. Okay. And again, the way you can convince yourself that this is really what is happening in this theory is that you can try to look at the Tooth anomaly matching coefficient. So again, the claim is that you started out in the UV with this asymptotically free theory of quarks, antiquarks, and gauge bosons and neutrinos. Yes, and the claim is that in the IR, it's just going to be a theory of these pure gauge singlets, these mesons and baryons. So no more gauge group, yes, but composite degrees of freedom. Okay, so if that's the case, then you should be able to match the global anomalies. And so this is again the thing that threw, I think, Seiberg off. I think that's what he said for a long time, that he tried to match the anomalies and they almost matched, but didn't quite match. Yes. And then he realized that, of course, the reason is because there is this quantum modification, which is going to tell you that at least one of these is going to have a vacuum expectation value. Yes, so either the baryons or the meson have to have a vacuum expectation value in order to match this quantum version of the constraint. So you should not try to match all the global anomalies at the same time. Yes, depending on which point you are, either at the baryon or the meson point. You know, it's in the baryon point. You know, the baryon number is spontaneously broken, so you should not match that symmetry. On the meson point, then, you know, the SUF cross SUF global symmetry is broken to the diagonal. So there you should only match the diagonal part. And then if you try that, then it all works out. Okay, so that's the story of the quantum modified constraint. And of course, you know, if this on its own is already pretty good, convincing argument, but that's not all. Yes, because you can now add a mass to one of the flavors and integrate it out, and lo and behold, of course, you recover the ADS superpotential out of this weird. So the X is just a Lagrange multiplier. It's just enforcing the constraint. Yes, but if you now add an extra flavor to a mass to one of the flavors, yes, then you can integrate out the one flavor in the theory with the constraint, and you will recover the ADS superpotential. Okay, so that's now it's starting to really look like, you know, everything is holding together. Okay. Now the other special case is when the number of flavors is equal to n+1. So in that case, that's what is called the S-confining case. So in that case, you know, sort of the most naive thing is the right description, which is now you take the mesons and the baryons as composites, but again, still, you know, just gauge singlets. And now all the Tooth anomalies are actually matched at the origin. So no flavor symmetry breaking or no symmetry breaking is necessary here. Okay. And so you can sit at the origin of the moduli space, but there is a superpotential term allowed here, which is allowed without necessarily breaking any of the global symmetries. So that one is, you know, the conjecture is that one is indeed generated, and that will actually just implement the equations of motion from this superpotential. Will just implement the actual classical constraints in the theory. Okay. So now, what is the actual phase of these two special cases? So we call this the screen phase, so that's partly why this S-confinement name stands for, yes. So this is one of those weird phases which looks like it's confining, yes, and in some sense, some of the aspects are there in the sense that studying the gauge theory, now you have the theory of gauge singlets, yes. However, you know, the true definition of confinement is that there will be a linear potential generated between the test charges. Now that's not going to be happening here, and that you can see that you shouldn't even expect that, because you started out with a theory where you have massless quarks, so you have dynamical degrees of freedom in the smallest representation of the gauge group, so you can essentially screen any test charge. So the right description for this phase is that actually, you know, this is a screen phase. You know, you can think of it either as a Higgs phase or a screen phase, depending on whether you're far out on the moduli space. Then you can think of this as, you know, the gauge group is just completely broken, and you know, the the mesons and the baryons will just describe the unequal degrees of freedom of your theory, or close to the origin, as you can think of those as some composite degrees of freedom, that this is what complementarity stands for, the fact that, you know, there's one phase that in different limits you can interpret differently. Yes, you can interpret it either as a Higgs phase, yes, or as a string phase. People usually still call it confining phase. You know, sometimes they call this one confinement. The F equals n+1. Seiberg called it confinement without chiral symmetry breaking, and F equals 1. We call it confinement with chiral symmetry breaking. But again, you know, here the word confinement doesn't stand for the technical definition, as the you know, the lattice people will tell us that, you know, the Wilson loop has an areal or linear potential between. It just stands for the fact that it's described in terms of gauge singlets, composite gauge singlets. Okay, so that was these special cases, yes. And then there are these two other big lines, big classes of theory, so that once you go above F equals n+1, but below 3/2 n, then you will get something that is called the free magnetic phase, and then above that you will get the conformal theory. Okay, so for both of these, actually, Seiberg discovered that a dual theory, a so-called Seiberg dual, exists. Okay, so this is what is called Seiberg duality. So this happens for the number of flavors is in this range. Yes, so for both of these, you know, there's a Seiberg dual. Okay, and what we found is that for the theory that we are considering, so this now we call the electric theory. So this is the original theory that we are trying to find out what phase it is in. There's a corresponding magnetic theory. Okay, so it's a gauge theory based on a different gauge group. It's called the Seiberg dual gauge group. Yes, with the same number of flavors. Yes, so the global symmetries, of course, have to agree. Yes, so the global symmetries, you know, there's nothing that you can do about it. That's an observable quantity. Yes, but the gauge group of two theories don't have to agree. Yes, the gauge variant quantities are not physically observable, so you know, they don't have to be the same. Yes, and what we found is that indeed, you know, these two theories actually will flow to the same IR. Okay, so they have the same low energy description. So they describe the same low energy physics. Yes, and he had very strong arguments, you know, to check that, you know, all the 't Hooft anomalies between the electric and the magnetic theory match. They have the same flat directions. You can move up and down in these theories by integrating out, fixing the theory, etc. So he made a very convincing argument that these two theories indeed have the same, they are corresponding to the same IR physics. Okay, and then the question is, okay, so then what is the phase? Yes, well, it depends on the number of flavors. So for a certain number of flavors, when it's just above the S confining but below 3/2 n, then you look at the magnetic gauge group, and it turns out that the magnetic gauge group, because here you just barely have more flavors than number of colors, so the gauge group is relatively small, but the number of flavors is relatively, you know, big compared to that. So that means that the magnetic gauge group is actually itself a free theory. Okay, so that's called the free magnetic phase. Okay, so in that case, you are going to expect to see free mesons, yes, and free dual quarks, and free gluons, and yeah, exactly, free gluons, free gluinos, yes, everything is free, yes. Very good. So you know, this is a very you know, very unusual effect, yes. So you have an emergent gauge symmetry here, yes. You started out in the UV with an SUN gauge group, and you ended up with a completely different gauge group in the IR, which you can actually observe. That's what you can actually observe, yes. So you will see those gauge bosons, you know, as some deeply interacting massless things, yes. So in fact, this is the first time when I saw this. This is the first place where I saw massless composite gauge bosons. Okay? And later on, actually, some of us use this. You have these composite gauge bosons in RS type composite Higgs models, etc. So you can actually get really a dynamical sort of toy model of a theory that looks like the standard model, but the W and the Z are actually composites. I remember, when I saw Seiberg first time give this talk in like '95, he said, if it ever turns out that the W and the Z are composites, remember, I said it first. Anyway, so you can see. So what you are going to have here is just it's just a free gauge theory essentially. Now, when the number of flavors is between, I'm sorry. So it's just it's just the Coulomb potential there. The coupling runs to zero. That's what I tried to write down. It's an ordinary Coulomb potential, yes, but the coupling ran to zero. So when R, yeah.
But is still like static force in the
Yes. I'm sorry. So I'm asking what is the potential between two test charges? Yes, and potential growth. I'm sorry. Test charges at a finite distance from each other. Yes, and so it's something it's at a finite distance, and of course it's not quite the complete IR limit yet. So that's the expectation for it. It's a Coulomb potential with a coupling that would want to run to zero but hasn't run yet to zero. We are the finite. All right. Now for the case between 3/2n and 3n, that's another interesting example. So again, you still have Seiberg duality. So both of these theories exist. They are well-defined gauge groups. And in this case, the claim is that actually both the electric and the magnetic gauge theory will flow to the same IR fixed point. So that in that case, the theory is at a conformal fixed point. So it's in the conformal phase, or often also called the non-abelian Coulomb phase, just in the Coulomb in the sense that, there are gauge, it's an interacting gauge theory, yes, but it's a non-abelian, it's not a U1 phase. So. And there are many arguments for why this would be the right thing. So close to the edges, when F is close to 3/2n, then there's a Banks-X fixed point in the magnetic theory. Okay. And when F is close to 3n, then there's a Banks-X fixed point in the electric theory. Okay. So that's a strong argument that in both of these regions, the theory should be conformal, yes. And then the expectation is that it's conformal everywhere in between. There are, other checks that you can do. There's something called A maximalization, which is telling you, how to calculate the dimensions of the operator. So all of that works pretty well. So this is, a consistent picture that has been pretty widely accepted.
So the superconformal index has been computed on both sides.
I'm sorry?
The superconformal index has been computed on both sides.
Yes. Right. All right. So that's the story of SUSY QCD. Yes. And it's again, it's a beautiful picture. Yes, but it's quite different from what we expect in non-supersymmetric QCD. Yes. So as far as we know, lattice simulations are only suggesting two different phases. Yes. One, the chiral symmetry breaking, the one like in QCD, SUF plus SUF, broken with the diagonal, you have pions, blah, blah. Okay. And for a large number of flavors, and this, I'm not quite sure, whether that's exactly known, but it's that boundary is, but it's at a pretty large number of flavors. It could be that it's actually higher than the highest flavor that we can test in the supersymmetric case. There should be a conformal phase. Okay. Very good. So we would like to start making some connection between the supersymmetric and the non-supersymmetric theories. Yes. So of course, what you want to do is you want to start adding supersymmetry breaking to Seiberg duality and start, calculating, what the phase of those theories are going to be. Okay, clearly that was one of the most important questions, and we were definitely not the first to start thinking about it. As I said, Seiberg's results were in '94, so to my knowledge, this was the first paper that tried to address that, like, right away, right after that, yes. But they said, okay, so let's perturb it with some, supersymmetry breaking terms on the electric side and some supersymmetry breaking terms on the magnetic side. But in the very first paper, this was just essentially some random guess. Yes, they didn't really, know how to connect these various parameters to each other. Okay, so it wasn't, so they had some, some of the phases seemed okay, but it didn't, again, this was sort of, a nice start, but not,
So what was S in that?
S, I think, is probably lambda squared. It's like, so this is like a soft mass for the quarks, and this is like a gluino mass for the. That's essentially what you want. Yes, you want to get rid of the super partner. So you will see AMSB does exactly this. The main thing is that, well, you see that it does it in a controlled way. Okay, so then, there were many other papers, they started to become more and more systematic, coupling into spurions and use holomorphy. Yeah, so that's of course the kind of thing that we want to do, yes. But for example, in the first paper, we still found the runaway direction for the ADS case. Now, Xinxia Cheng and Yara Shadmi were the next who started, seriously considering this, and they did start considering this as a version of gauge mediation, and then try to actually calculate, what the soft supersymmetry breaking terms are, both in the electric and the magnetic side, and it was pretty nice. They calculated, because it was coming from gauge mediation, they were able to get some of the soft breaking terms using some RGs, and they found the runaway direction for the case of the duality either in the squark or the meson. Okay, so and the symmetry breaking pattern wasn't quite as expected in QCD. Now, later on, there was a lot of effort by Nima and Ratazzi and Marcos and Ratazzi. So they were trying to map the soft breakings by coupling it to a background anomalous gauge field, gauge U1R and supergravity. So this is now starting to become very similar to what we are interested in. However, what they did is they ignored the pure anomaly breaking effects, anomaly mediated SUSY breaking effects, yes? And that's what we will be actually trying to do. So again, it's wasn't quite exactly what getting the theory that we are interested in. Then a very most systematic approach that we were aware of. So that was by Zohar and Steve Abel and Matt Buican. What they found is that the conserved currents were actually easy to exactly map through the duality, and they were trying to find all the SUSY, relate the SUSY breaking terms to some conserved currents and find, the corresponding neutral currents in the IR. So it was some sort of a systematic way of starting to derive, what the corresponding SUSY breaking terms on the electric and the magnetic theories actually are going to be. Okay, so they found some results that were pretty similar. Okay, so they did still find baryonic runaway directions and breaking patterns that were not like in QCD. So what we would like to do is, have a method that where essentially all aspects of SUSY breaking are under control. And I don't mean that I can take the SUSY breaking to be very large, but at least you know what exactly the mapping from the electric to the magnetic theory is. All aspects of that are going to be under control. Okay, and then the question is, you know, are we going to get some symmetry breaking pattern similar as QCD or not? Yes. So this is what, you know, Hitoshi started to really push through. So we are going to be using anomaly mediated supersymmetry breaking for perturbing the Seiberg dualities. Now, one caution here is that, you know, anomaly mediation originally was designed, in some sense, yes, to give you a specific implementation of the MSSM, where, you know, we are thinking of this pure as a true model of the BSM, like at the PV scale, etc. Yes. But here, that's not the meaning in which we are going to be using anomaly mediation. Here, we will simply use it to study, you know, just the phases of gauge theories, and we are not thinking of this as an actual BSM model. Yes. So that's how we are going to be thinking about anomaly mediation. And again, you know, the assumption here is that SUSY breaking is mediated purely by supergravity, and there will be no direct interactions between the SUSY breaking sector and the matter sector. Okay, so this is something, again, you know, that initiated as a theory of BSM because it gave very particularly nice and predictive theory for the pattern of the soft supersymmetry breaking terms. This was called at some point, you know, RS0, yes, because also first written down by Randall and Sandrum before Randall and Sandrum, before the theories that became known as RS. And so this is a different paper, yes, and then also Cidic-Luti, Murayama, and Bertazzi, and later on also minima and Bertazzi. Okay. So we are assuming, again, the matter sector is sequestered. There's no direct interaction with supersymmetry breaking generated, and the only source for supersymmetry breaking will be the auxiliary field of the supergravity multiplet. And the best way, so this is the way we are going to be using this, is this description by Pomerol and Bertazzi of anomaly mediation, is via the introduction of the Weil compensator phi. This is a conformal compensator, and you can use this as a spurion for super Weil transformations. Okay, and the effect of supersymmetry breaking will show up through the coupling of this compensator to the Kähler potential and to the superpotential. And so this compensator, again, is then going to have an auxiliary field. So this is going to be our SUSY breaking parameter. Okay, so this is really beautiful now, yes, because you can really see what all the effects of supersymmetry breaking are in a theory with an arbitrary Kähler potential and superpotential, yes. And through this compensator, I can actually follow through, you know, the effects of supersymmetry breaking, because there is this principle that is telling you, you know, how at the low energies, you know, the supersymmetry breaking will manifest itself, and it's going to be independent of, you know, that's what is also really nice about AMSB, is that it's independent of the UV of the theory. So when you just go to, you know, a strongly coupled theory, just from the IR, you will be able to find, you know, what the supersymmetry breaking terms in that theory are actually going to be. So let's just see an example. Yes, let's say the matter sector is conformal. Yes, if the matter sector is conformal, for example, you know, you just have, you know, phi cube superpotential and at least classically, yes, and a canonical Kähler potential. Yes, you can actually scale out the compensator from the theory. Yes, you can just rescale your superfields by the compensator. Will completely remove the compensator, and there will be no supersymmetry breaking. Yes, so supersymmetry breaking will be tied to the violations of conformality. Yes, and so this will be a UV insensitive process. So
I understood you, sir. So you've got the supersymmetric theory on one side, it's coupled to supergravity, and supergravity is also coupled to something else. Is that it?
well, so So there will be supersymmetry breaking, yes.
What
And
is the basic? Where is the breaking happen?
So it is, yes, right here. Yes, only
Right, so this looks like supergravity is coupled to your
some supersymmetry breaking sector, yes. But that one again, is not going to play any role for us, yes. So we are only going to be interested in how does supersymmetry breaking manifest itself in our sector.
Yes. But the source of that breaking was.
But the source of that breaking was this sequestered whatever. Yes. But again, the beauty of this whole story is that I will never have to eventually rely on supergravity anymore on what the SUSY breaking sector was at all. Yes. Because everything is going to be captured just by this one spurion, this vauca compensator, yes, which has an auxiliary field.
This comes out with some analysis.
Yeah. So this is the Pomarov Ratazzi, that was the right.
So the effect of that earlier setup can be summarized on this other theory.
Exactly. Right. And then the other beauty of it is, yes, sorry, that the other beauty. Let me just say that now, of course, what we are going to be interested in is having both an electric and a magnetic version of that theory, yes. And then I'm going to couple this spurion both in the electric theory and in the magnetic theory. And because I have this very definite prescription of how to couple the spurions, and that again, they are tied to essentially all the violations of conformality, yes, I'm going to be able to map the SUSY breaking both to the electric theory and to the magnetic theory. But that's not, it doesn't mean, so I'm not talking about this versus that, yes. So this part of the theory I'm never interested in, yes. But what I'm saying is the effect of this whole thing could be, very simply captured, through these simple spurions, which then I can check its effects both, on the electric side and on the magnetic side, including the effects coming from the Kähler.
And the Kähler potential and the superpotential you wrote in the next transparency.
Right.
Those are the Kähler potential, superpotential of your
So this is the Kähler potential, the superpotential of the matter sector. Yes. And then the effect of this hidden, all this stuff that I'm just going to put in a black box is just going to be through this very simple inclusion of the of these vauca compensators.
Sorry.
All right. No, it's okay.
So it's somehow like a lucky break that it's such a simple modification that comes from this specific break.
Right. So exactly. So I mean, that's why this is we think this is probably the best way to try to perturb it. Yes, because this one again, it's UV insensitive, so you really, it doesn't really matter, what the theory was at high energies. You can sort of confidently calculate, what the low energy effective theory is at a given scale, including the effects of supersymmetry break. And that's very special. It's very special about this theory. Yes. So this is not a,
is this an illusion of why the effect through this supergravity mediation is so simple?
I guess it's it's coming from super conformal supergravity. It's the scaling variance. But you can see essentially, yes, there is it. Yes, so you see that essentially this is like it's like a vauca compensator, and it's all just coupled to the dimensions of the various operators. So that, yeah.
Is the supergravity coupling very weak? Is it classical supergravity?
That's a good question. I don't know.
Probably, right? Because the loops of the supergravity introduce non-locals.
Right. All right. So once we have this whole setup with the anomaly mediation, yes, then we can just go ahead and calculate, what the various forms of supersymmetry breaking terms are going to be in my theory, yes, and So basically, I told you that wherever you have breaking of scaling variance, there will be some form of supersymmetry breaking effect. So if you have any RG running, that is going to generate for you some soft breaking terms. Yes. So the running of the gauge coupling is going to generate for you gaugino masses. Yes. The running of the Yukawa interactions, yes, they are going to give you soft scalar masses and A terms. Okay, so for example, now this is the really cool part here, yes. So for example, if you look at SUSY QCD, yes, the example that we are interested in, yes, you're going to get a gaugino mass, yes, and then you are going to get squark masses, which are exactly proportional to 3n C minus NF. Okay, number of 3 times number of colors minus number of flavors. This is the quantitative that is exactly positive in the region where the theory is asymptotically free. Yes, so for asymptotically free SUSY QCD is going to give you positive squark masses plus gaugino masses. So that's exactly the kind of perturbation that we are interested in, that would sort of start lifting the supersymmetric theory towards the non-supersymmetric version of QCD. Of course, you know, M is a SUSY breaking parameter, so it's within a limit. You don't want to make the SUSY breaking parameter very, very large, because then you will lose all your control over the theory. Yes, so you know, this will be SUSY QCD, which is perturbed for the massless spectrum to actually agree with ordinary QCD, but it doesn't mean that it is ordinary QCD, because all these other particles are still there. They are just a little bit heavier, but they are still there below the scale of confinement. Okay, so this is what I was just telling you. The loop-induced terms give you massless spectrum exactly like in ordinary QCD. Now, if any of you remember the AMSB version of the MSSM, actually it was very problematic, yes, because you had slapton masses that didn't couple to the right-handed slaptons. They didn't couple to a non-abelian gauge, only to an abelian one. So they actually were tachyonic, yes. But here we are only, but that's not a problem for us, yes, because we are only interested in asymptotically free gauge groups. So we will get a perfect UV boundary condition in the sense of, you know, all the sparks and the neutrinos that they had it. Okay. Now, one other important thing, so that's something that wasn't really pointed out previously, that if there is a superpotential that is not scaling variant, of course, you will also get a contribution to the supersymmetry breaking term. So it's not only the RGs that are going to give you AMSB effects, but the tree-level superpotential can give you potentially a tree-level effect, the tree-level supersymmetry breaking effect. Okay, and you can find, you know, what the effect is if you have a general. So this is assuming a canonical Taylor potential. If you have a general Taylor potential, then this is going to be the expression for the SUSY breaking, for the tree-level SUSY breaking.
That's the Taylor potential of the theory of interest.
So, exactly. So this is the Taylor potential of the theory of interest, yes, of SUSY QCD, yes. And now what is this? Yeah, so that's going to be a question, yes. So sometimes you know it, sometimes you don't. So sometimes, you know, still, you know, I'm running out of time, but at least I hope I get to some of those cases where you will find that, you know, you do all of this, and yet the theory is not calculable. Okay? You know, there's nothing wrong with the method, whatever. You know, it's just not calculable. So it's not a guarantee that, you know, this is a guarantee that, you know, you get a perturbation in the right direction, but it's not a guarantee that you will be able to then find what the result is. Okay, but let's show some simple examples. Okay, so this is the simplest and nicest one. Yes, let's say when the number of flavors is less than the number of colors. So this is the case that I call the ADS superpotential. Yes, and now here's the beauty. Yes, because you have a tree-level superpotential in this theory, which is not scaling variant, meaning it's not cubic. It will actually directly generate a term in the potential for these meson fills. Okay, so now you can add this to the potential that is generated from the superpotential. It comes with a negative sign, all beautiful, yes, and it will actually stabilize the ADS superpotential. Okay, and again, this is one of these weird things, yes, because it's formally tree level, but it's really some non-perturbative effect that includes the SUSY breaking in the theory, yes, because it's has the ADS superpotential, it has sort of the instanton factor in it, and has supersymmetry breaking. So this is the kind of stuff that looks really hard to calculate, yes. But AMSB tells you what it is, yes. So this is very nice, yes. So if you just have the ADS superpotential, yes, you would have this runaway theory, yes. And now, actually, together with the AMSB, there will be a minimum at a finite value. And the symmetry breaking pattern will be along this direction, will be exactly like in QCD. So as you will have the chiral symmetry breaking, and there will be some master degrees of freedom, of course, but they are the pions. And it could be like
So, correctly, you took fine with non-zero supersymmetry breaking scenario. You calculated your superpotential.
right. So there is this superpotential, yes. Now this directly gives the potential, yes, just because we're from the F terms, yes. Plus there is this term that comes from supersymmetry breaking.
Yeah, so when you turn on SUSY breaking,
I turn on, so little m is always the SUSY breaking parameter.
right? And then you are trying to take the m to a different part and eventually continue to different part.
Well, I mean, really, strictly speaking, I take m to be very small. I will always assume that m is much smaller than lambda. Okay. Now it would be really nice. It would be really nice if I could take m much larger than lambda. Yes. I mean, it's tempting, but we really don't know. All I can say is that
larger than lambda, then you are solved.
then you would have solved it. Yes, but
the question is that when you go from zero to non-zero, I mean.
Oh, from zero to non-zero, yes. So that we assume that you can, that
there is no extra condition.
But there is no exactly. I can take it. I mean, if I take it, infinitesimally small, that there wouldn't be a discontinuity. Yes. So that's an assumption that there's no discontinuity. All right, very good. So let me just, I'm running out, but let's just say a few things that.
Previously, you said something special happens for analytical NC-1 in the specific case.
Well, so what was special about NC-1 was that particular case could be calculated via instantons. But that was but the phase was the same for NC-1 down to 0. Okay, and here we see the same thing. And in fact, I'm going to try to argue that actually you're going to get the same phase everywhere, essentially. Just like in QCD. Okay, so let me, okay, so some of these arguments are pretty involved, so maybe I'm not going to go through that, even though that's what I spent my last 2 days on writing, but okay, so there are the special cases when you have the quantum modified constraint. And so this is the first case when the baryon is actually showing up. But this makes it actually much more subtle to analyze, yes, because in this case, some of the vectors have to be large. Yes, you know that there are some large vectors here. Yes. So that means that the higher order corrections in the Kähler potential, if I have something like m dagger m squared, yes, is not suppressed. Yes, because what would it be suppressed by? It would be suppressed by lambda. Yes, that some of the vectors must be of order lambda. Yes, so we did actually. So this is my student. Did this Andrew Gomes a pretty nice and involved analysis for what happens for these special cases. Yes, and he found some things that are really nice. How many Goldstone bosons there have to be in the theory along particular points. For example, along the Meson point, there the Meson is getting the diagonal of that. Yes, so that there have to be some Goldstone bosons. Those have to have positive kinetic terms, etc. But Okay, so this is the Meson point here. So here you can go ahead and calculate what the potential is. And the mesons are indeed stable at the point, the normal point where SUF plus SUF is broken to the diagonal. However, the baryons are uncalculable. And the reason is that, you don't really know what their Taylor potential is. In fact, there are two different parameters that you can do there. And depending on this ratio alpha and beta, in some directions, you may have runaway directions, and in some other directions, you don't. The theory is strongly coupled. You simply cannot say along this point, if there is a runaway direction or is there no runaway direction. So, and then you can also go ahead and check the baryon. And again, it turns out that the direction of the mesons is uncalculable due to higher order terms, potential higher order terms in the case. Okay. There's a special case here that when the number of colors is equal to 2. In that case, actually, you can show that the ordinary, because the global symmetry breaking pattern is different, because for an NC is equal to 2, you really have an ST theory and not an SU theory. So you have a bigger global symmetry and a different breaking pattern. And anyway, so in that case, it works. Okay, so now this is the one case that I would like to really point your attention to. So this was the most subtle case. And previously, people claimed that there was actually a calculable runaway direction in this theory. Yes? And what we found is when we did the analysis very carefully, including the loop-induced supersymmetry breaking terms, then actually the runaway direction is lifted. Okay, so maybe I'm not going to go through this because I'm running out of time, or I have already run out of time. But again, I just want to argue that this is a case where it didn't have to be calculable. Yes, you have these uncalculable coefficients again in the superpotential or in the Taylor potential. But we went ahead and we calculated it, and it was actually pretty involved, because now you have baryons, but you have mesons, and you don't know what the maps of the baryons versus the mesons are. So you have several parameters. So you have to generically write down what the potential is along this direction, including the supersymmetry breaking terms. And so we did all of that, and then checked all the possible directions and found that the direction that the baryon number is conserved, so that the little b is 0. So that would be the normal VAD. So that's the VAD, the QCD-like VAD. So we found that in fact has a stable minimum. But the only way you could show it is that you take into account the loop-induced terms for the soft breaking terms. Okay, and similarly, for the baryon number breaking direction, if you naively calculate it, it looks like there is a runaway potential there along the baryonic direction, and that was sort of the generic expectation that once you start getting baryon, there will always be baryonic runaways, and you won't get anything predictive out of these theories. By the way, baryonic runaway wouldn't necessarily mean that the theory, the vacuum of the theory is at a very large value. It would just mean it would push the theory towards VAFs that are of the order of lambda, and then of course you don't know what happens there. And anyway, but what we were able to show is that these baryonic runaways actually don't happen. And again, this was another very subtle argument. You have to include the loop-induced, the two loop-induced effects. And the really funny thing was that this was something that was left out previously, because they said, oh, it's 2-loop and the other one is 3-level. And of course, we are talking about small perturbations around the origin. So there, the scaling as a power of the VAF is more sensitive than having like a 1/16 pi squared factor. So it turns out that actually this 2-loop AMSB potential is capable of lifting, at least close to the origin, the baryonic runaway direction. So what we found is that, okay, so this is the runaway, and this is the 2-loop, and it's actually going to dominate. So pretty nice. Okay. Now for the free magnetic theory.
So the origin was stable.
The origin was stable, exactly. The origin was stable, and there was a QCD-like minimum there. SUN cross SUN broken to the diagonal. Okay, so QCD-like. That's the actual global minimum of it. But is it really global? We don't know. Yes, because there could be other minima close to lambda. Yes, but at least in the region of the origin, that was the lowest minimum. Okay, free magnetic phase. So that was another interesting direction. Again, people said that there will probably be all kinds of baryonic runaways. You won't be able to say anything. Turns out that's again not true. It turns out that as long as at least the lower end of the free magnetic phase, not quite the entire free magnetic phase, we can show that there are no baryonic runaway directions. Okay? And again, we have to check several different branches. The mesonic branch, a mixed branch, and the baryonic one. Oh, what's going on? Come on, I didn't do this. It was something with this.
Slides.
It was just telling me to finish, yes? Okay. But even if I start playing this now, sorry. So I should just unplug this, yes. Otherwise, it's gonna keep hurting me. So let me just tell you what the upshot is. Which slide are we at? Let me show you this slide here. Okay. So what we found is, again, we went through the whole table of SUSY QCD a la Seiberg, and we found QCD-like. This is non-calculable, but the QCD-like vacuum is there. QCD-like in the top of the free magnetic phase and the bottom of the conformal phase. There could be possibly runaway directions, but the QCD-like vacuum is definitely there. And then the top of the conformal also QCD-like. So it's really suggested, yes, that all of these weird Seiberg-like SUSY phases, as soon as you add a little bit of perturbation, yes, they will just disappear and they will all go into QCD-like phases. Okay, so in that sense, we are finding sort of agreement with our naive expectation that the non-supersymmetric gauge theories, they have sort of two different phases, either QCD-like or conformal. Now the conformal would probably start somewhere over here, yes, but it's not accessible via AMSB, yes, because there the theory is not asymptotically free. Okay, so let me basically stop here. Let me just say that we did a lot of other things that I will not get to, the chiral gauge theories, and there we're able to use this method for AMSB to find new kind of candidate symmetry breaking patterns. So the simplest chiral gauge theory is take an antisymmetric tensor plus for SUN with F-4 antifundamentals. And people had some guesses for what the symmetry breaking pattern is for that back from the late 70s, Banks and Saskind and Dimopoulos, those people, actually Stuart Rabi maybe also. So they found a truth anomaly matching for that theory. And what we find is that actually that's not, when we do the supersymmetric theory, that's not quite what we are getting. We are getting something very similar, but instead of having just a single condensate, we have to postulate two condensates in order to get the symmetry breaking pattern that supersymmetry is trying to tell you. So we did all of these SU5 and then SUN with antisymmetric, even flavors, odd flavors, look at all their, I'm not going to go through that. And then we also did the symmetric tensor, again, so that one has a very weird duality found by Pulio and Strassler back in the mid-90s. And again, we found what the symmetry breaking patterns of those theories are. And then another interesting application was doing the SO series. And again, the reason why this one was interesting is because this one can have true confinement. Because if I take SO with a vector, yes, so then, it's not the smallest representation. The smallest representation is the spinner. So you have the possibility of actually having a truly confining theory here. And in fact, that's what we found. So we did go through, so there's a similar table for the SO theories, and I'm not going to go through that, but there is one key one, the abelian Coulomb phase, and here you're actually getting a massless monopole. Okay, so this is a little bit more like the Seiberg-Witten theories. This particular one, you have SOF with n-2 vectors, because that breaks down to SO2, which is a U1, which is an abelian Coulomb phase, yes, and that had a massless monopole. So we were able to show, at least for all these lower number of things, that you're actually going to get ordinary confinement with monopole condensation, and that's the mechanism for confinement for the SO theories. All right, so I'm out of time, so let me just summarize. Okay, so supersymmetric gauge theories are of course fantastic to find the vacuum structure of the theory. AMSB appears to be a somewhat superior method, and again, it may be just a little bit of a coincidence, yes, but it just gives you exactly the things that you want without much sensitivity to the UV. So it's pretty predictive. Usually gives results that can be connected nicely to the non-supersymmetric phases, and many of the weird non-supersymmetric phases are disappearing if you add a little bit of perturbation. Okay, we found new symmetry breaking patterns for the chiral gauge theories. I didn't have time to go through that. And again, we also established confinement and chiral symmetry breaking via monopole condensation in many of these SO theories. All right, thank you very much, and sorry for going over.
Maybe from the online participants have any questions?
Yes.
So thanks for this. You talked about moduli of the initial mesons and then how would it tetra box and tetra box?
I'm sorry?
How would it stay that the tetra box and tetra box?
Oh, so this is, as you know, so this is a supersymmetric theory. Yes. So these are, in here, it's just rigorously established that these are the moduli theory. Yes. These are all the directions that that are parameterizing the bottom of the potential that you get in supersymmetry. The specific potential is called the B term. So that's that's just a mathematical theorem that it's just given by these holomorphic gauge invariants. And you can just enumerate them and find which are the independent ones. So here there is no question. Is there a pentaquark, or I mean, those would, yeah.
What I'm really asking, you have modifications in potential and
Where I mean, so I can of course add more kinds of chiral superfields, yes, but as long as it's SUSY QCD-like. Yes. So if you don't add weird representations, then it's just mesons and baryons. Okay. Now, if you add weird representations, yes, like antisymmetric, etc., then you can get all kinds of weird gauging variants out of it. Yes? So that's a game that I used to play when I was a student, to try to analyze these supersymmetric gauge theories. So there, those things happen, but again, the reason why you have these other invariants is because you will have like an antisymmetric, and then you have a Q bar, Q bar, yes? Or you have a 3-index antisymmetric, then you can have different kind of contractions, yes? But again, as long as it's just QCD-like, then the mesons and baryons are the only degrees of freedom. To parameterize the moduli space of the theory. It doesn't mean that there's no dynamics that would ever bring up, some weird more composite object. Yes. I mean, so the fact that you have mesons and baryons parameterizing the moduli space doesn't mean that those are the true degrees of freedom of the strongly coupled theories. In fact, there's only one case, yes, which is this S-confining case. There is exactly all the mesons and all the baryons are the true degrees of freedom of the theory. Yes. Everything else is complicated. Yes.
Was that phi field that you had, wasn't the overall scale like the y factor of the metric?
So again, so it's a it's a compensator, so it's a spurion, yeah. So it's set eventually to 1.
But it wasn't one of the supergravity modes.
I don't think so. It's a compensator. Yes.
But it seems to be
It's a spurion, yes. It's a spurion that is telling you how to, how to translate the effect of supersymmetry breaking from, from the, onto the visible sector.
It seems to couple just as you said, couple the scale,
Right.
breaking of scale in there.
Right.
That's exactly how the scale factor of the metric would couple.
Right.
I was wondering if there was some way of thinking that.
Okay, it's possible. I don't want to,
And I was wondering that if that was the case, if you could just then, couple this theory to supergravity
right,
and choose to work in a background, supergravity background
Right.
that breaks it.
right,
Then just forget about all this other supersymmetric breaking sector and so on. You take your theory,
right.
couple it to supergravity and choose to work in a supersymmetric breaking.
Okay.
And then that's your setup. The background is killing one because there's some sort of
Yes, yes.
to do it on both sides. The duality work.
Interesting. Okay.
And then you could have classically scale breaking terms of like R square. You're saying that it should only have W square.
Yeah, I mean, any dynamics of the supergravity.
Right.
This is just a background
For this field theory.
But then the surprise is how come it should be the scale factor of the metric that
Now
goes.
you can set that background to whatever you need. You choose to turn on the scale factor of the metric 1 plus n squared.
Right.
What stops you? You do that. The nice purpose is universal because it's the metric. So how it couples.
Right. Exactly. Okay. So you're saying that you have another way of doing this?
No, I don't understand that, but I was just thinking that.
No, I understand.
So your AMSB, even though it's much more minute, but it's still sensitive to your UV. In a sense, the value of F5 that you are taking that does have some information about your sequencing information.
Sorry, you mean the value of
The compensated rate that you are
Right.
taking to get the scale of your, let's say, gravity mass and things like that.
right?
That does have an effect of, because at the end of the day, you're trying to solve, let's say, SUSY condition, and that's why you are translating the wave of some SUSY breaking piece wherever it is happening into your F5, right? And that is what's giving you, then you forget about it, and that's what
Right,
brings you the wave of the other state.
Right.
But the thing is that where you evaluate this situation, it has a scale dependency.
You mean the value of f itself?
The area itself, yeah.
Right. But, so that I take as a free parameter. Yes, that's what I'm varying. Yes. That's my little m essentially.
So in the sense, when you say UV insensitive, it's not entirely UV insensitive.
Fine, it depends on this parameter, yes.
Right, which is actually insensitive. If you tell that you
Right.
are going to change.
Right, but that sensitivity is kept, yes. So
The sensitivity is.
I mean, I keep m as a free parameter, yes, everywhere.
Right.
I guess what I meant is that the form of supersymmetry, form of all the SUSY breaking terms, yes, can be pinned down
Yes.
from this one spurion.
So what I meant is that I'm not because if I actually at the end of the day I plan to write it in terms of like pi f pi as in terms of coming in
Right,
the primordial phase matter supersymmetry is broken.
right,
So there you introduce an fx, and there you have to put in a square root of zx to get into this.
right.
But you're saying that I don't care.
I don't
because
care.
They convert it into a non.
Exactly. I don't exactly that's my approach, but I just don't care. All of it is going to be packaged into this one number, and I mean, if you tell me it's 5 times as much, I just say that okay, I change all my other parameters so that it can become whatever I want it to be. Yeah.
So as long as I keep my scale of renormalization scale and move EF and N space, then yes.
Right.
Okay, so if there are no further questions, can you?